Today is August 21st, 2026. This research overview is AI-generated, based on a partial daily collection, and requires human review before its claims are reused. Across 26 included paper analyses, the strongest theme is that progress increasingly comes from changing an agent's environment, workflow, memory, or tools, rather than its underlying model weights. But the day's clearest warning is methodological. A system can look successful according to a visible score, while still failing the task that actually matters.
The sharpest example comes from scientific software repair. A new benchmark contains 119 repository tasks across 20 scientific domains, using public tests plus hidden semantic checks. The best configuration passed only 47.90% of tasks exactly, even though its average public test score was 96.64%. That is, measured evidence within this benchmark, not proof that public tests are always misleading. Model and agent harness effects are also entangled. Still, the result says visible test success can miss scientific boundary conditions, integration defects, and regressions.
A terminal command study reaches a related conclusion by holding generated replies fixed and changing only how commands travel to execution. Adding one parser erased between 55.4 and 73.2 percentage points of success across the tested configurations. Correct escaping restored all 448 public raw path outcomes examined. This is unusually direct evidence that transport, quoting, and reparsing can cause failure after the model has produced workable content. The editorial connection to scientific repair is useful but limited. Both favor executable final state checks, yet they study different tasks and should not be numerically compared.
Task construction and environment adaptation offer two responses. One system synthesizes terminal tasks by grounding instructions, solutions, verifiers, and containers in the same realized state. Training on 1,200 successful trajectories improved 3 Quen model sizes. The 9 billion parameter model rose from 27.34 to 35.58 on the reported terminal benchmark. Another system wraps trusted, resettable environments with state changes, action transformations, and task chains. On a software benchmark, its combined skills reached 54.30% success, with fewer average steps than using no skills. Neither result establishes transfer to live, irreversible services.
Several papers push improvement into persistent external structures. SkillEvo edits textual support skills using verified multi-turn failures and reports 81.8% held-out task success versus 66.4% when feedback was reduced to single-turn questions. Governance limited document growth to 2.8%, compared with 16.2% without it. FlowEvo instead compiles verified workflows into executable skills, while hierarchical self-improvement evolves whole task harnesses around a frozen model. These are complementary designs, not evidence that one caused another. Important caveats include private data, narrow domains, limited replication, and dependence on checkable outcomes.
Memory complicates that story. On an adversarial diagnostic benchmark, every tested memory strategy performed worse than using no memory. For Gemini, the best memory result was 71.17% versus 85.16% without memory. For Quen, it was 70.13 versus 81.83%. Yet another study found that retaining full attempts plus informative correctness or executor feedback raised a 6 benchmark average from 66.8 to 79.3%. The apparent tension is not a contradiction. One benchmark deliberately plants harmful histories, while the other supplies useful feedback and selects the best result across repeated iterations.
That suggests a concrete research question. Should memory influence every answer, no answer, or only answers where a risk gate predicts benefit? A strong experiment would compare always use, never use, prompt-gated, and learned-gated memory on both ordinary tasks and trap-heavy tasks. It should report a selective risk curve rather than one average. Similar discipline is needed for policy compliance. Policy Guide raised mean workflow success from 0.42 to 0.62, but it remained advisory, used simulated English domains, and imposed more than 5 times the wall clock overhead.
Robotics divides into long horizon planning and dexterous grasping. A hierarchical robot model kept its low-level controller fixed, but used uncertainty-triggered world model search for high-level decisions. On book organization, success rose from 6 of 10 trials to 9 of 10, while progress increased from 66.67 to 93.33%. That is promising but imprecise because each condition had only 10 physical trials. A separate exploration system reports better simulated learning when vision-language-guided successes initialize residual reinforcement learning, but exact graph values were unavailable, and its success detector used privileged information.
For grasping, 2 systems learn gripper-centered contact priors without training on object meshes, then adapt them to unseen objects. One reports 86.93% average simulated success across 3 robotic hands, but lacks aggregate physical trial success. The topology condition system can request different contact patterns and beats a topology-aware comparison on filtered pairs, yet its absolute success remains low and trails several unconditioned planners on a broader object set. The measured trade-off is therefore between semantic control and stability, not a universal win. Repeated real trials should vary mass, friction, visibility, approach pose, and requested contact pattern.
Adaptation papers also show why accuracy alone is incomplete. Greek language supervised training changed strong Greek trace fidelity from 0 qualifying traces out of 5,156 base outputs to roughly 97 to 98%. Reinforcement learning later reduced fallback formatting from 24.1 to 2.5% and eliminated answer channel leakage in the controlled study. But the authors do not establish a defensible accuracy gain, and script identity is not the same as fluent or faithful reasoning. Another staged method for internalizing document knowledge improved both domain and general measures in 7 of 8 settings, though each checkpoint had only 1 training run.
Systems and media results occupy very different regimes. Sparse prefill attention delivered up to 17.54 times the dense baseline speed in reduced precision comparison, and 30.49 times in the reported lower precision operator setting, at long context on an H2O GPU. Scores stayed close to full attention, but this covers prefill, 1 accelerator family, and specific workloads. TinyCast fits probabilistic forecasting into about 146,000 parameters and runs a 48-step call in 4.08 seconds on a microcontroller. Yet its nominal 80% interval covered only 60% at long horizons. These numbers should never be compared directly.
The concise takeaway is that execution paths, retained capabilities, and hidden failure mechanisms deserve equal status with headline scores. The strongest next steps are matched executable evaluations, calibrated memory gating, larger real robot trials, multi-seed adaptation studies, and hardware portability tests. Remember that this was a partial daily run, with recurring missing table cells, private data, model-based judges, unequal compute or resolution, and narrow evaluation sets. For the paper-level evidence, qualifications, and links, continue to the linked daily summary for August 21st.